Welcome to this lecture on animal behavior. Today, we are going to explore two of the most fascinating and visually striking concepts in evolutionary biology: sexual dimorphism and mate choice. We will discover why males and females of the same species often look completely different, and how the high-stakes game of choosing a partner shapes the incredible diversity of traits we see in the animal kingdom. Let us dive in. To begin our journey, we must first understand what sexual dimorphism actually is. Imagine spotting a magnificent bird with a massive, iridescent tail, while its female counterpart is plain and brown. This phenomenon is formally known as sexual dimorphism, which literally translates to two forms. It refers to the distinct physical differences between males and females of the exact same species. But why does this happen? It arises because males and females face entirely different evolutionary pressures. While females typically invest massive amounts of energy into producing a few high-quality offspring, males often invest their energy into developing traits and weapons that help them compete for access to those females. Now that we know what sexual dimorphism is, we must ask why it is so crucial to study. Understanding these physical differences is absolutely vital because it acts as a visible map of a species' social structure. Whenever you observe extreme differences between sexes, you can almost guarantee that the species has a highly competitive mating system, such as polygyny, where one male mates with many females. Without this concept, we would be completely blind to the powerful evolutionary forces shaping the animal kingdom. Furthermore, these physical differences often reduce direct competition for food between males and females, allowing the entire species to exploit a much wider range of environmental resources. Now that we understand the evolutionary drivers, let us look at how we actually measure this difference. The formula for the sexual dimorphism ratio comes from a simple comparison of physical size. D represents the sexual dimorphism ratio, which is a pure number with no units. M subscript M stands for the average mass of the adult males in a population, and M subscript F represents the average mass of the adult females. When the male mass increases relative to the female mass, the ratio D becomes much greater than 1, which physically indicates a fiercely competitive, male-biased mating system. If the ratio is exactly 1, it means both sexes are the same size, pointing to a monogamous system. Let us apply this formula to a concrete example using the southern elephant seal. We're given the average adult male mass of 3,000 kilograms and the female mass of 900 kilograms, and we need to find the dimorphism ratio. We choose this formula because it standardizes the size difference into a single comparable number. First, we identify our variables and plug them into the numerator and denominator. Notice how the units of kilograms cancel out perfectly, leaving us with a pure ratio. The final answer is 3.33. Physically, this massive number means males are more than 3 times heavier than females, indicating intense physical combat for mating rights on the beaches. Before we move on to another example, let us visualize what this extreme ratio actually looks like in nature. On your screen, you can see a clear comparison between the male and female southern elephant seal. On the left is the massive male, weighing in at 3,000 kilograms. On the right is the much smaller female at 900 kilograms. The large arrow connecting them highlights the sexual dimorphism ratio of 3.33 that we just calculated. This diagram teaches us that such a drastic physical difference is not just a number. It represents a biological reality where only the absolute largest males can successfully defend a territory and secure mates. Having seen male-dominated dimorphism, let us look at a scenario where the females are larger. In the golden silk orb weaver spider, we are given a tiny male mass of 0.5 grams and a female mass of 4.0 grams. We need to calculate the ratio to understand this reversed dynamic. We use the exact same formula, and it is crucial to always keep the male mass on top to maintain a consistent standard. We substitute 0.5 for the male and 4.0 for the female. The units of grams cancel out. The final answer is 0.125. Physically, this decimal fraction proves the male is only 1/8 the size of the female, which happens because females need massive energy reserves to produce thousands of eggs. Having explored how sexes differ physically, let us look at the behavioral mechanism that drives many of these differences. In the animal kingdom, choosing a mate is the ultimate high-stakes decision because it directly determines the survival of an individual's offspring. This process is formally known as mate choice, or intersexual selection. Because females produce large, nutrient-rich eggs and provide the bulk of parental care, they are the limiting resource in reproduction. Therefore, they must be incredibly picky. They carefully inspect males, looking for honest signals of health, genetic quality, or the ability to provide resources. This intense choosiness forces males to evolve elaborate displays just to win their attention. This mechanism of choosiness leads us to an important realization about evolution. Mate choice is fundamentally important because it explains the existence of traits that would otherwise seem like a terrible idea for basic survival. Take a peacock, for example. Its massive tail makes it slow and highly visible to predators, which completely contradicts basic natural selection. However, because peahens exclusively choose to mate with males possessing the most spectacular tails, the reproductive benefit of having that tail far outweighs the survival cost. Without the concept of mate choice, we would have absolutely no scientific explanation for the evolution of complex courtship dances, vibrant plumage, and intricate bird songs. This concept of choosiness leads us directly to a mathematical way to measure mating competition. The operational sex ratio formula comes from comparing the exact number of individuals ready to mate at any given moment. OSR stands for the operational sex ratio. NM represents the number of sexually active, receptive males ready to mate. And F represents the number of sexually receptive females available at that exact same time. It is important to note that if the number of competing males increases while the number of females stays the same, the OSR becomes heavily male-biased. A high OSR physically means males face fierce competition, which drives the evolution of intense mate choice by the females. Let us see this formula in action with a concrete example of a wood frog chorus. We are given that there are 120 croaking males and only 15 receptive females present at the pond on a given night. We need to calculate the operational sex ratio to understand the mating dynamics. We choose this formula because it reveals exactly how many males are competing for each available female. We substitute 120 for the active males and 15 for the active females. We only count sexually active individuals to accurately reflect the competitive environment. The final answer is 8. Physically, this tells us there are 8 males competing for every single female, meaning the pond is highly chaotic and females hold all the power of mate choice. Before we look at an exception to this rule, let us visualize this competitive imbalance. On your screen is a diagram showing a seesaw tipped heavily to one side. On the left, you see a large cluster of 8 frogs representing the abundant competing males. On the right, elevated side, sits a single frog representing the scarce, receptive female. This visual perfectly captures the high operational sex ratio of 8:1 that we just calculated. The diagram teaches us that when the ratio is heavily skewed, the biological balance of power shifts entirely to the rarer sex. The males must compete intensely while the single female gets to be highly selective. Now that we have seen a typical male-biased system, let us calculate what happens when biological roles are reversed, as seen in seahorses. We are given that there are 40 females ready to deposit eggs, but only 10 receptive males available because most are already pregnant. We need to calculate the OSR for this unique situation. We use the exact same formula to easily compare this meadow to the frog pond. We substitute 10 for the available males and 40 for the available females. Notice how the number of males is now much lower? The final answer is 0.25. Physically, this means there is only 1/4 of a male available for every female. Because receptive males are the limiting resource, the traditional roles flip and males become the choosy sex. As we wrap up this lecture, let us review the most important ideas we have covered. First, sexual dimorphism is not random. It is a physical manifestation of evolutionary pressures that maps out a species' mating system. Second, mate choice is the ultimate evolutionary filter, ensuring that reproduction is a highly selective pursuit of genetic excellence rather than a random event. Finally, mathematical tools like the dimorphism ratio and the operational sex ratio allow us to perfectly predict and quantify these complex social dynamics. You have now mastered the fundamental forces that create the stunning diversity of animal life. Great job, and keep exploring the fascinating world of animal behavior.